And then I'm just going to denote the generators of the fundamental group as follows. So there's the base point x0. If we go around this way, I'm going to call that S, and if we go around this way, I'm going to call that T. And then we calculate the following. So what's the boundary map delta 2? Well, let's see. We want to see it's going to map to some coefficient to each of the two one handles. So let's say this is the alpha coordinate and this is the beta coordinate. Let's have a look at what happens with the alpha one. Well, first of all, you take the path to the center of the 2 cell, the 2 handle, so that's going around here. Then from there we go to each of the intersections with the alpha 1 handle, so we either go here or we go here. So let's say we go to -1 first, so we choose a path that goes around like this. Then we go from here into the center of alpha and then back along gamma alpha. So what we've done is we've got a loop that's gone around here, gone there, and then back. And we can see that this is trivial in pi 1 of W. So we just get the sign of this intersection point, -1, with the trivial loop. What about the other intersection point? Well, for this one we have to go round the hole. From this point we have to go around this way and enter the core and then back there. So this actually gives us a non-trivial loop in pi 1, which is the loop I denoted by T, and we get the sign +1 from the intersection. So we get T -1 is the component of the boundary map to the alpha part of C1. And then similarly, we get S-1 to beta. The S coming from the fact that we went over here, and then we had to go to the +1 side of the handle. Well, this is the bottom part of this strip. We can't get to that this way without leaving the 2 handle, so we have to go underneath to get to it before then going back along this path. So we've gone through the hole once and back, and that's the generator S. And then going over the top, we just get a trivial loop again with the sign -1. Then, by the same reasoning, delta 1 of H1 alpha is 1 minus S, generator H0. And if we apply delta 1 to the beta 1 handle, we get T -1, lots of H0. So let's just put this all together and see what we get. For ease of notation, I'm just going to denote Z pi 1 of W just as lambda, just to make this a bit shorter. So we have lambda generated by H2 maps to lambda generated by H1 alpha, direct sum lambda generated by H1 beta maps to lambda generated by H0. This is our relative chain complex given by the handle decomposition. We put the boundary maps in, get T -1, S -1 here, and then 1 minus S, T -1 for that one. So let's compute the homology of this chain complex. First we look at this map. I claim that T -1 and then hence S -1 is injective. Now, I should have said that the group ring lambda is Z of Z squared, and general element in this this group ring looks like some sum coefficient aij t to the I, s to the j for the generators t and s for the fundamental group, and this is a finite sum. And for this to map to 0, so if this is in the kernel, so we've got something here, if this maps to 0, then by the map t minus 1, say, we'll just look at the first component. What does that tell us? That tells us then alpha aij has to be the same as a I minus 1j for all the terms to cancel pairwise to give us 0. But this is a finite sum, so when you get to the end you've got one of them equaling 0, hence all of them equaling 0. So this tells us that aij has to be identically 0 to be in the kernel, so this proves injectivity. Same argument shows for s minus 1, so this is injective. Okay, so that being injective tells us that, well, h2 has to be 0 because the kernel is 0, and it also, we've got the same maps, roughly speaking, coming out of here. So this is again injective, so we get nothing here for h1. So the only case of slight interest is h0. Well, h0 is going to be z generated by t plus z generated by s, all generated by h0, quotiented out by the image of this. Well, what's the image of this? This is saying, roughly speaking, that s equals 1 and t equals 1 in the image. So if s and t both equal 1, we lose these generators and we're just left with the integers, which is the z part from the z pi 1, and they're generated by h0. And a remark, this is good because this agrees with what we observed earlier. This should just be the normal homology of the universal cover with z coefficients. What's the universal cover? Well, this is R2. And we know the homology of R2 is just, well, unreduced. We just have a copy of z in dimension 0 and nothing else, which is what we observed. And last thing before I finish is there's an exercise. It's to do similar computation with do the same for m fattened wedge of spheres, S1 wedge, S2, viewed as a cobordism between the empty set and the boundary of this. So when I say fattened, it's precisely this picture. So here's the S1 fattened to a solid torus, and then there's this sphere, so there's a hollow, there's a ball scooped out from the inside, and there's the fattened S2 there. Or rather, that's W. And you can do the same for this with 1 0 handle, 1 1 handle, and 1 2 handle. And this example isn't quite so trivial. There's something a little bit more interesting going on, and that's the end of the lecture. Any questions?
Is the cobordism from a sphere to a torus?
Yes, or the empty set to the disjoint union of a sphere and a torus.
Okay. Is that helpful in some way?
It's just the way you want to build it up. I want to build it up by first starting with a ball. So we've attached a ball to the empty set, so we started with the empty set. Then I want to attach a 1 handle. This has now given us this torus. And then I want to attach a 2 cell. And this gives us this hole inside here. I want to build it up like that, from the empty set to now have both boundary components as M prime on the top. But of course you can do this in different ways. Any other questions?
So this contracts to the wedge again, so the universal colour is a line in the spheres.
Yeah. So you should get homology
You know
of
what you
that.
should get.
You know what you should get, yeah. But getting that with Z pi 1 modules is a bit more interesting. All right, that's it.
Okay.
Cheers.
You can cut that out.